All right, we're at section 3.3, energy in a magnetic field. Let's share the PowerPoint. Now, if you recall, we started last time. We started with a, a equation for Kirchhoff's loop, where E minus IR minus L di dt equals 0, and we're going to use that same equation here. Only we're taking the negative parts to the other side. You can still see the E IR plus L di dt, but we've multiplied both sides by I, so that when we end up with IE equal I squared R plus Li d dt. So the UB is the energy stored in an inductor. So dUB dt equals Li di dt. And so the UB equals the integral of dUB equals the integral of Li di from 0 to I. We can take out the L because it's a constant. So L, the integral from 0 to I of IDI is equal to the integral from 0 to 1 of 0 to I of IDI is equal to 1/2 I squared. And that's the indefinite integral. If you substitute, of course, 0, you get 0, and you get I, you get 1/2 I squared, and it's all times L. So the energy stored in an inductor is 1/2 Li squared. Okay, so let's from equation 31.5, which is in example 31.1. So look at that example. The inductance of a solenoid is L equal mu 0 n squared V. And the magnetic field of a solenoid, equation 29.7, is B equal mu 0 n I. But now we're going to change that. B equals mu 0 n I, where I is equal to B divided by mu 0 times mu 0 n. So UB equals 1/2 Li squared. We take the L and we substitute the mu 0 n squared V, and we take the oh, I lost my place. We take the I, and it's B over mu 0 n, but it's I squared, so it's B over mu 0 n squared. And you'll see that the n squared cancels the n within the parentheses, the n squared within the parentheses, and you have a mu 0 divided by mu 0 squared. So you end up with the energy stored in a magnet is equal to B squared divided by 2 mu 0 V. And then the magnetic energy density, small ub, is equal to ub u sub b divided by v, and that's equal to b squared divided by 2 mu 0. Okay, let's see. You're performing an experiment that requires the highest possible magnetic energy density in the interior of a very long current carrying solenoid. Which of the following adjustments increases the energy density? Now you can choose more than one choice. You can increase the number of turns per unit length on the solenoid, or you can increase the cross-sectional area of the solenoid, increasing only the length of the solenoid while keeping the number of turns per unit length fixed, or increasing the current in the solenoid. Well, it certainly, let's see if we have if B is equal to mu 0 Ni, you can see that if you increase N, B will go up. If you increase I, B will go up. So really it's A and D. If you increase the cross-sectional area, you'll actually diminish it. If you increase the length, you're diminishing the N per unit length. So that would decrease it also. So it's A and D are the are the answers to that. Now, that ends this section on energy in a magnetic field. We'll go on with mutual inductance in the next section.